Hi everyone, and thank you for joining me today for Data Analytics, Architectural Patterns and Best Practices. My name is Rada Stanic and I'm a Principal Solutions Architect in the Enterprise team based in Sydney. Today's session is a collection of answers to the most frequently asked questions by my own customers. I attempted to address those over the next 30 minutes, and in order to do that, I have framed the session with the following agenda. We will first talk about current data challenges and trends, and in that context, we will highlight the importance of having a suitable data governance framework. Before diving deeper into key architecture patterns, we will have a look at some AWS analytics services and how they fit in the various stages of the data analytics pipeline. That will lead us into deeper discussion around common architecture patterns. In the end, I will leave you with advice on how best to approach architecting solutions for your own business problems. So with that, let's get started. I have categorized challenges and trends into three key areas. Firstly, we are dealing with an explosion of data, and while this has been the case for the past decade or so, we now have not only a velocity and volume to deal with, but also an unprecedented number of sources from which data is coming. Some examples are social media, IoT sensors, various data logs, and so on. In addition to explosion of data, we also have explosion of personas. We have an ever-increasing number of different roles that are participating in building an end-to-end data analytics operational pipeline. We have data stewards responsible for governance, data curators, data engineers, developers, machine learning experts, and data scientists, as well as business and data analysts. That is a lot of roles, and the challenge presents itself here on how do we provide best tools for all these jobs and make these people productive. Finally, last but not least, businesses are demanding faster decision-making, which has to be based on real-time data insights. So the challenge becomes, how do we provide these insights in real time while dealing with large volumes of data? My goal today is to provide you with the architecture and design patterns that will help you address these challenges in your own environment. Before we go deeper into technology, it is key to highlight the importance of data governance as an overall framework that is particularly helpful in addressing those challenges around the explosion of data and also an ever-increasing number of business personas. Data governance is 80% related to people and processes and 20% technology. I will briefly touch on three different approaches. We can have centralized approach, which is typically adopted by organizations with well-developed data analytics practice and strong executive sponsorship. In this instance, we have an enterprise-level data governance organization, or a DGO, which has framework in place, and it cuts across all different business units, such as finance, engineering, marketing, and so on. This enterprise DGO has a deep understanding of different business units' needs and has established a framework that addresses those needs. DGO is able to enforce guardrails and guidelines that come with an effective data governance framework. At the other end of the spectrum, we have the centralized approach, which is the most commonly adopted. In this model, we have DGOs established at the individual business unit level rather than an enterprise level. And finally, we have federated approach as the middle ground. Here, we have a centralized DGO which is making the best effort to understand needs of different business units without having deep enough understanding across all of them. The result is the best effort set of guidelines without strict enforcement. The key message here is that having data governance in some shape or form is an absolute must. As I mentioned in the beginning, before we dive deeper into specific architecture patterns, it is necessary to have a look at some of the key analytics services and what they do. So let's take a quick look. If we start with the ingestion phase, we are really talking about either real-time or batch, so we would typically be using services like Amazon Kinesis Portfolio, whether it's data streams, video streams, or Kinesis Data Firehose. In some cases, we also may be using managed streaming for Kafka, and I'll discuss how you can make those choices later. You also now have the capability to do batch processing for data stored in SaaS applications such as Salesforce with services like Amazon AppFlow. Moving along into data processing phase, we can leverage tools such as AWS Glue to build an effective ETL, extract, transform, and load process. Or we can leverage services like Amazon EMR, Elastic MapReduce, which can be running any one of the open source frameworks on top. Spark on EMR is a great example. It is in this phase that we can leverage serverless technologies such as Lambda functions to create event-driven workflows. AWS Glue Data Brew is a notable new addition to analytics services which allows those without deep coding skills to quickly prepare data sets for various use cases by leveraging built-in transformations. When we are talking about data lake itself, then the centerpiece of data lake is S3 object storage, durable and cost-effective storage layer. Services such as lake formation allow us to establish an effective governance and fine-grained security and access controls within our data lake. Finally, with AWS Glue Data Catalog and crawlers, we can discover data schema and catalog all metadata, which will help us query data in the lake as well as across external data sources. When it comes to data analytics part of the pipeline, this is where the querying capabilities are very important, as well as the ability to visualize and search the data. We can leverage Amazon Athena for ad-hoc queries, Amazon QuickSight for visualization, and Amazon Elasticsearch for searching various log data. Lastly, in this phase, we also use our cloud data warehouse, Amazon Redshift, in order to perform queries on the business data that is stored in the warehouse. And finally, with the ever-increasing importance of machine learning, to establish future predictions and business modeling, we can use the outputs of our data analytics pipeline to build various ML use cases. For that, we can benefit from any one of the pre-built ML managed services. This is a very, very brief overview of the key services and where they sit within the analytics pipeline, just so we can effectively reference them as we dive deeper into our key architecture patterns. I have no intention to claim that we will address all possible patterns, but we will attempt to share with you the most commonly asked for ones. The first one is an emergence of a lakehouse architecture. So the question I'd like to address is why we are talking about lakehouse architecture. I mean, isn't data lake enough? And how would you build one on AWS platform? I wanted to show you this evolution first that will then lead us into some logical conclusions about benefits of the lakehouse approach. Traditionally, everyone used data warehouses, where you basically ingest data from various online transactional processes, ERP, CRM systems, data from different lines of business. All this data goes into data warehouse, and then we visualize it in some form of dashboard. Next, industry started talking about data lakes, and this is where Amazon S3 comes in play as the basis for a cost-effective, durable, and scalable data lake. A lot of enterprises combine data warehouses and data lakes. We can perform queries that span across the data warehouse, where you keep your business data, and S3, where we can have raw and unfiltered data, for example. So why would we need something like a lakehouse, and what does it give us that we don't have already with warehouse and data lake? On the right-hand side, I'm trying to show that with the explosion of data, we need to have very specific custom data stores, such as relational databases, non-relational databases, custom data stores for big analytics, data stores that allow us to do big data processing at scale, data warehouses, and then also data stores for machine learning use cases. Lakehouse architecture is focused on giving us the ability to move data with ease in different directions. Firstly, from the inside out, from the data lake to the custom data stores. Secondly, the ability to move data from the outside in, from the custom data stores back into the data lake. And lastly, the ability to move data around the perimeter between different custom data stores. Now that we understand what's the goal of the Lakehouse architecture, let's have a look at a possible example of how we would build one on AWS. We've touched on this already, that Amazon Redshift is our cloud data warehouse. So imagine an enterprise with multiple business units, such as business, marketing, sales. It's common to have a need for data separation between these units, so we would run 3 separate Redshift clusters, one for each business unit. And let's say that we have a need to share data between these units, so with the newly available feature of Redshift, we can do things like data sharing, where we can share data between these clusters without having the need to copy it from one cluster to another. This is a great example of benefits of the Lakehouse approach. And with this kind of architecture, we can also query third-party data that is sitting in the external data sources as well as data in the S3 data lake. We can do that by leveraging services like Redshift Spectrum, which can combine queries across the data warehouse itself and the S3. Hopefully, this example helped illustrate how Lakehouse architecture, powered by Redshift data sharing capability, helps us minimize data movement. The next architecture pattern that I wanted to touch on is how to perform ad hoc SQL queries on my data lake. If we briefly revisit a concept of data lake, we have something that we call AWS Glue Crawler that will scan the data in the lake as well as the transactional stores, and it will populate AWS Glue data catalog, which is a source of all metadata for the entire data landscape. Once the data is cataloged, we can apply fine-grained access control to the tables using lake formation. It is then that when we can use Amazon Athena to query both the external tables and the data in the lake through the catalog and access data without any movement. Finally, we can visualize the data in Amazon QuickSight, where analysts can author and create data sets by running these complex queries in Athena. We can store the output in a scalable cache called Amazon Spice for fast analytics. One of the main benefits of using Athena is that it's based on serverless technology and it scales based on number of users and queries. Let's have a look now at another design pattern that allows us to combine queries across data lake and cloud data warehouse. Here, building on top of Athena ad hoc queries, what we can further do is create a data set by combining data in Amazon Redshift and Athena, and then store the output in Spice for fast analytics and visualize it in QuickSight. I hope that you can see how easy it is to extend one design pattern and build the further capability through additional services while leveraging data stored in different places and all with minimal movement. Next, we have one of my favorite patterns, and the reason why it's my favorite pattern is because it's attempting to clearly articulate which tools are best suited for a specific job and role. This addresses that second challenge that I touched on in the beginning on how we deal with the explosion of business personas and job roles in the data analytics space. This is a simplified representation to help you see the mapping between tools and job roles. Once the data is ingested in the lake and we want to do some ad hoc processing, then the job roles such as data curators and data scientists typically need to do some quick validation, cleaning, and enrichment before they are able to build their own use cases. And even though they may have coding skills, typically people in these roles do not want to do too much coding in order to process data. That is where services like AWS Glue Data Brew provide nice visual interface and more than 250 built-in transformations that allow them to prepare their data without having to do any coding. Similarly, with Athena, they can do quick ad hoc queries. When it comes down to data engineers and developers, these are typically the job roles with deep coding skills, and ideal tools for them are services like AWS Glue, which allows the creation of complex and sophisticated ETL jobs. Data analysts and business analysts will leverage Amazon Athena and Redshift as a cloud warehouse to prepare the data sets that need to be visualized in various dashboards. Finally, services such as Amazon QuickSight are ideal for business analysts and data curators who are focused on various dashboard creations. QuickSight is also greatly useful to developers who can now embed these dashboards within their applications. I mentioned already that the question I get asked a lot is how I create flexible ETL processes, and there are hundreds of different ways in which you can create an ETL process. What I decided to do here is to show you something a little bit creative. What I'm trying to articulate is the flexibility that comes with using serverless technology such as step functions and Lambda and combining them with data analytics tools like AWS Glue. Before we dive into the example itself, conceptually, the main flow of events starts with an AWS step functions state machine. This state machine defines the steps in the orchestrated ETL workflow. A state machine can be triggered through Amazon CloudWatch based on a schedule. As the state machine execution progresses, it invokes the ETL jobs. As shown in the diagram, the invocation happens indirectly through intermediary AWS Lambda functions that you author and set up. We call this type of function an ETL runner. Now, in this particular example, we are showing step functions as framework, where we're doing parallel processing of sales and marketing data so that we can join and combine that data together in the end. This architecture allows for an expansion with further parallel workflows which can be added in the future. Processing of sales and marketing data in this particular example can start and finish at different times based on when data becomes available. Similarly, preparation for data joining will only start when all parallel activities are completed. In summary, as the data becomes available and its schema is discovered by crawlers, Lambda function triggers the first Glue ETL job to perhaps clean that data, deduplicate it, change the format if required. And then another Lambda function will call a second ETL job, which in this case is done by EMR. So this is really a simple example of chained ETL jobs and effective use of step functions to allow for parallel workflow execution. The next design pattern shows how to move on-premises data to a cloud data warehouse. This is a simplified view of loading data warehouse. We could do a whole presentation based just on the part that talks about the ingestion or migration of data from on-premises environments to Amazon S3. For that, we use services like database migration services, various Snow family devices, and connectivity services such as Direct Connect and site-to-site VPN. Let's assume that we've chosen the right method and we've ingested data into Amazon S3. Once the data is in S3, we can have AWS Glue scheduled to clean and transform the data, format it appropriately, And we can also add a degree of complexity by adding data that's coming from relational database such as Amazon Aurora. I'm trying to illustrate that you can easily enrich the data that came from the on-prem environment with data that we have in a cloud already. Then we load that combined data as tables into Redshift and run daily business reports via QuickSight. Let's have a look now at how do we make data accessible to machine learning experts and data scientists. By now, I'm hoping that you are able to recognize some of the previously discussed patterns here. Data sources in this pattern can be logs, relational, non-relational databases, streaming data, data coming from on-premises. We are using Glue to perform ETL and store data into raw data bucket. It's always the best practice in any analytics pipeline to preserve raw data so we can subsequently manipulate it and transform it in a way that is suitable for many different use cases. Once we have data in this raw format in an S3 bucket, we can use Glue again to transform it in any particular way. We are calling it here cleaned and enriched data. Perhaps all we've done is we've deduplicated and combined it with additional sources that we have in the cloud. Finally, just as an example, we are then splitting here into two separate branches. In the bottom part, we could be doing some transformations to create suitable training data sets so that we can run services like Amazon SageMaker to build, train, and deploy machine learning models. And in the loop, in the top branch, we are transforming data so that we have bucket with extracted features that various managed services can use to perform specific use cases. We are now approaching last couple of architecture patterns, and this one is about doing batch processing. I have shown two examples here. We would typically store data from our sources into staging environment, and then in both illustrated examples, we can use Lambda function to notify our chosen batch processing service that data is available. That will trigger either Amazon EMR or AWS Glue to process and transform that data and upload it in the Redshift. Both examples perform batch processing, and which one you choose will depend on the type of data transformation and processing that is required. Now, let's have a look at how do I process stream data in real time. At the start, I said that one of the big challenges for businesses today is desire to gain real or near real-time insights into data. Here we are capturing sensor data and using Kinesis Data Firehose to collect streaming data, and then we are building stream processing layer by leveraging Kinesis Data Analytics. And since we want to store this data somewhere, we will leverage Kinesis Data Firehose to store that streaming data into what we are calling serving layer. Once we have data available in the S3 serving layer, we can query it and display it. Finally, a lot of customers are asking the question if they can combine batch and stream processing by leveraging the same data source, and the answer is yes. Let's assume we are collecting sensor data again. We are using Kinesis Firehose to capture raw sensor data, and for the batch processing layer specifically, we will store the raw data in S3. Once in S3, we can use Glue to combine captured streams with device settings and store that transformed data in the S3 bucket represented as a serving layer. Similarly, the stream processing layer at the bottom is showing how the same source is being handled using stream processing services such as Kinesis Data Analytics and Kinesis Firehose. Captured stream data is stored in S3. From here on, we can query and visualize it. As you can see it's quite easy to implement batch and stream processing on the same source of data. I have talked to you about multiple services being available to solve the same problem, so it's only fair that I give you some guidance around making that choice. Speaking of streaming, as we just did, my customers frequently ask if they should use Kafka or Kinesis. The answer is quite simple. If you have very deep integrations with other AWS services in place, then Amazon Kinesis is an ideal choice. If, on the other hand, you've used Kafka for quite some time and you are keen to use the open source technologies and deep third-party integrations, but you want to avoid dealing with infrastructure and high availability setup, then using Amazon Managed Streaming for Kafka makes a lot of sense. When it comes to serverless, if you are implementing stateless use case where we are dealing with event-driven architectures, then using Lambda makes a lot of sense. In case of stateful use cases, Kinesis Data Analytics is the right choice. If you are looking to process data at scale with significant infrastructure and flexibility required, then EMR is the right choice. Finally, if we want to move real-time data from point A to point B, then it makes sense to use Kinesis Data Firehose for that. Since this session is all about design patterns and best practices, we must finish by drawing your attention to well-architected framework. AWS Well-Architected helps cloud architects build secure, high-performing, resilient, and efficient infrastructure for their applications and workloads. It is based on 5 pillars: security, reliability, performance and efficiency, cost optimization, and operational excellence. We have, over time, extended well-architected framework so it can provide a specific lens in addition to core pillars. It can be a serverless lens, or as I'm about to show you, analytics lens. From the security point of view, analytics lens would guide you to ensure that you are performing proper data classifications and granting the least privilege for different users. From reliability point of view, it is about ensuring that your analytics pipelines are designed for resiliency and that your ETL jobs can fail and that mechanisms are in place to deal with these failures. Analytics lens also helps ensure that you have established process for governing data changes, using optimal file formats and partitioning, as well as choosing optimal storage and compute solutions. From cost optimization point of view, it is important to delete unused data and to have lifecycle policies that ensure optimal storage is used. Additionally, if you are running EMR clusters, make sure that spot instances are used appropriately. From an operational excellence point of view, we want to be monitoring the health of our analytics pipelines. In conclusion, I wanted to leave you with some key considerations as you embark on your analytics journey in the cloud. Firstly, I would say that you shouldn't try to solve and build for the future all at once. Instead, always start by architecting for your needs only and for the specific business problem in hand. At the same time, it is key to always architect with the end in mind. By doing so, your starting patterns will be easily extensible and you won't be restricted with your future choices. Thirdly, always choose the best tool for the job. This will help with people's productivity and operational excellence. Next, as we've just discussed, always perform the well-architected review with the analytics lens. It will help you follow the best practices. And finally, establish an effective data governance model, because without it, you will not be able to address the first 2 challenges I mentioned in the beginning. Those are the explosion of data and the explosion of the business personas. Before we completely wrap up, I also wanted to draw your attention to a number of training and certification options available to you to broaden your knowledge and to get certified in the data analytics space. In the end, I sincerely thank you for joining me today, and I'm hopeful that you have gained some knowledge that will inspire you to experiment and solve data analytics use cases in your organization. I also thank you in advance for taking time to complete the session survey. Your feedback means a lot to us. Thank you.